My name is Ron Marianetti. I'm a software engineer here at Grok, and I'm going to talk about swarming and how you can run a swarm on a machine and the internals of it and what it does. So we're going to talk about swarming. I'm going to talk about how to run a swarm on a laptop or a desktop machine, and also some of the internals of swarming, how it determines the best model and things like that. So we'll go a little bit into the algorithm later on in the presentation. So what swarming does, swarming is a process that determines the best CLA model for a given data set. It determines a number of things, both which components should go into the model, so which encoders, the spatial temporal pooler, which type of classifier information, things like that. It also, for each component, it determines the best parameters for that component. So when you run a swarm, you're providing a data set that it's going to optimize over, and you're telling the swarm operation what are you trying to do with this data set. For example, you might say, I'm trying to predict consumption field 4 steps in advance. You can also supply a custom error metric, which will be used to evaluate the effectiveness of each model, and swarming uses that to determine which model is the best as it's running. The output from the swarm is a text file. It's a description.py text file that can be in turn fed into the OPF, which is an online prediction framework. This text file has everything you need to completely describe the model. So behind the scenes, what swarming is doing is it's building up and evaluating typically hundreds of models in parallel. You can run it on a machine using just one process, or 32, depends on how big your machine is. The swarming outputs the best model, and by best we mean the model that produced the lowest error score. So we're not weighing anything else other than the error score. So a typical swarm is trying to evaluate many parameters, and it's typically a very huge search space. So the intelligence comes in, and how does it reduce that search space and try to find the best model as quickly as possible. For example, you might have, in your data set, you might have 5 optional fields you want to consider. There might be a couple optional model components to consider. There might be 15 scalar parameters and 4 enumerated parameters, etc. So there's quite a bit of things to be evaluated. So as swarming runs, what it does is it dynamically adjusts where it's going to search next based on results that it's achieved so far. So it's dynamically willowing down the area that it needs to search as it progresses. So an example of what you might feed into a swarm is shown here. Your data set is a bunch of records. Each record is on a row in a file, and the columns represent the fields that you have. So in this example, showing a data set with a timestamp field, a temperature field, and a consumption field. So that might be a typical thing you'd feed in. The swarm description that you provide might say something like, I want to aggregate records hourly. In this case, you can see the records are every 15 minutes, but the swarming process can automatically aggregate those into hourly records for you. I might say I want to predict consumption 2 steps in advance, and since I'm aggregating hourly, that'll end up being 2 hours in advance. And I might tell it to consider all 3 of these fields in my data file. So I will run a demo here to kind of show you what happens if you want to run swarming on your machine. Everything you need is in the NuPIC repo, but you do need to have a MySQL server available. The default settings are Swarm is going to look for a server on localhost with a username of root and an empty password, which is the default credentials you get when you install it for the first time. But if you need to, you can edit those credentials if you already have a server running somewhere else. So to run the demo, I'm going to run this command line and just kind of show you what happens when we do that. I'm going to get up here a CPU monitor so we can see what's happening on the machine. Yeah. So I'm going to run swarm, search stat.json, and I'm going to tell it to use 8 processes on my machine. Okay. So it's starting the swarm now, and it'll print out to the screen messages, kind of show you what's happening. You can kind of see here how many models have been evaluated so far. And since I told it to use 8 workers, you can see that all 8 cores are being heavily utilized right now. This swarm is a very fast and simple swarm just for demo purposes. Typically these models won't complete that fast, but you kind of get the idea of what's going on here. And then when the swarm completes, it'll print a summary at the end, just telling you this is information about the best model that it found, the various parameters that it chose, and it tells you it saved some information to your directory that you're working off of. And I'll go into more detail on what it produces there. But we evaluated, let's see, about 73 models in that particular run that took about 40 seconds.
How does it decide when it's done?
It's as it's running through the different field combinations, it actually adds more and more fields in as it creates more and more models. And once it gets to a point where adding more fields doesn't improve your error score, then it decides to stop. Okay, so this example that I just ran, I'll go more specifics of what was in the input that I gave to the swarm. So this particular data file was this format. It had, so the data file that you feed it, it's expected to find 3 header rows at the top. First one is your field name, second one is the field types, and third one is the field flags. But other than that, it's a standard CSV file. I skipped a slide. Okay, so you feed a swarm 2 things, a swarm description file and a data file. So the swarm description file is a JSON formatted text file, and it has kind of meta information about the swarm that you want to run. At a high level view, there's a section that tells which fields from your data file that you want to consider as part of the model. A stream definition, which contains the name of the file that you're going to feed in and the amount of aggregation you're going to perform. The inference type that you're doing, this is the type of model that you want to create. And I'm going to just talk about prediction models here. Inference args provides the name of the field that you're trying to predict and the number of steps in advance. Iteration count is the number of aggregated records you want to run through the model. And swarm size, you can tell it how big of a swarm to run, and that'll impact how long it takes, of course. You'll typically probably run a medium swarm. There's also an option to run a small swarm, which is kind of more of a smell test, just to make sure the flow is working right. And once you're willing to wait longer, you can run a large swarm. That'll take quite a bit longer, but you can often get a better model that way. I'm just going to walk through one of these files in more detail. So this is a typical JSON file that you would feed in to run Swarm. And here's some of the sections that I just referred to in the slide. Included fields, the fields that you want to consider as part of the Swarm. StreamDef has information about your input data, so the file name that you're going to use and the aggregation information. Inference type is multi-step in this case because we're doing a prediction model. Here we're telling it predict one step in advance, predicted field is consumption, use all the records in the data file, and run a medium swarm. So this is basically the gist of what you have to feed in to run Swarm. And I already went through the data file format a little bit. Okay, so now I'll start going into more internals of swarming and how it leverages multiple processes to run faster. So the more processes you have, you give it, the faster it can run. It runs in each process. It runs a model, so it means it can run that many models simultaneously. Nomenclature. Every process we're calling a swarm worker, and the way things are architected, each swarm worker is an equal citizen, and there's no central coordinated process. So the one of the benefits of this design is there is no single point of failure. You can actually these workers can actually come in and leave in the middle of a swarm. It'll still continue running. They communicate through a database. So all coordination is managed through the data in this database. And I'll talk a little bit about how that is happening. Yeah. So a typical swarm worker has, I'm going to walk through some pseudocode of what it's doing at a very high level. It fetches the latest model results from the database. So remember, all workers are publishing their results to this database. So a worker comes online, it can get what are all the latest results. So for each model that has been evaluated, we have the parameters and the error score that model produced are in this database. So given the current stage of the swarm and the history of all the model results so far, this worker can now make a set of parameters for a new candidate model. And I'll talk a little bit later on about how it does that. So it'll then create a new entry for this model in the database. It'll instantiate it, run it, and then as it's running, it actually publishes periodic results to the database. And then finally, when it's completed, it'll put in the final result of this model. So the swarming, I'm going to go a little bit more about the swarming algorithms now, and this is basically how does a worker figure out which model should try next. So there's a number of things that have to be determined. One of them is which input fields the model is going to use. Another is which components should be in the model, like which encoders you're going to use, what types of encoders. Are you going to have a spatial and temporal pooler? You could actually decide what kind of classifier you might want to have in there. There are different types of parameters that can show up for each component. You could have scalar parameters or enumerated parameters. So there's two kind of styles of parameters that need to be searched. So to determine all this, there's a kind of a family of algorithms that are used. For scalar parameters, we use particle swarm optimization algorithm. For enumerated values, we use a custom algorithm, and I'll talk a little bit more about that later. And then for determining which fields are in the model, we use a custom field search algorithm. So I'm going to go into those as well. First, the PSO, particle swarm. Again, this is used for determining the best value for scalar parameters. The rough idea behind PSO is you scatter a bunch of particles throughout the parameter space. When you run a media swarm, it actually allocates 5 particles. When you run a large swarm, it'll make 15 of them, so you get a little better valuation that way. But they're scattered around the parameter space initially, and each one is a model, essentially, and it runs the model, it gets an error score. So from that error score, we can decide where the particle should move. So where it moves is a combination of what is the global best among all the particles so far, and what is the local best that this particle has seen. So it kind of uses a weighted sum of those to figure out where it should move in the parameter space. So a particle will move to another position, and we repeat, so that they're continually moving through the space in that way. And the idea is eventually they'll kind of all gravitate towards hopefully the global min. That's the goal of these. So a little more details on how that is accomplished is we initialize each particle with a random position and velocity. Each particle has a record of its best position to date, meaning which position was I in that produced the lowest error score. At every location, we measure the fitness of the particle, and that's basically what was the error score on the model. And among all the particles, we also maintain the global best. So that is kind of a global position. Now, when we move a particle, its new position is evaluated in this manner. So v is the velocity of the particle. Just kind of a rough overview. This is saying my new velocity is going to be based on my old velocity plus some weighted, a random component plus some weight times how far am I away from my local best. So if I'm really far away from where my local best was, I'm going to move faster. Plus some weighted component of the global best. So if I'm really far away from the global best, I'm also going to move faster. So this is determining how fast I'm going to move in the next step. And my new position is my old position plus that velocity. So each particle is using this kind of method to figure out where it's going to move next. Intuition is basically they're moving in a direction that blends the local and the global best. And there is a random component because the space isn't always smooth. There's local minima, and you want to have some randomness in there so you don't get caught in one of those. This is a little demo that shows the goal of PSO. So we have a bunch of particles scattered all over the parameter space. In an ideal world, they wouldn't get caught in any local minima. They would all kind of gravitate towards a global minima. And so they're moving around the space. Eventually, they'll all settle in on where's the best position. In the real world, they don't always do that, but it does pretty well in most cases. Okay, so that was how we're finding scalar parameters. Now I'm going to talk about enumerated parameters. This would be an example of, say you had to figure out what type of encoder to use for a particular field. There might be 3 choices. You might have a regular scalar encoder to choose from, a delta encoder, or an adaptive encoder. This is kind of a contrived example, but gives a flavor for what's going on. You might also have an enumerated parameter which says whether the spatial pooler should be learning should be enabled or not. So that could be true or false. For these type of parameters, PSO doesn't work well. because there's no linear movement through space. So for these type of parameters, we use some custom logic here that what it does, it builds up an average error score for each choice. So if we've run, for example, we've run with a scalar encoder a few times, the average error score we got when we ran with scalar encoder was 0.1. When we ran with a delta encoder, the average error score was 0.2, etc. When we create a new model, we choose a new enumerated value using a weighted probability. And what we do is we give the one that had the lowest error score, we're most likely to pick that for the new model. So we just kind of weight them inversely proportional to the error scores.
But initially it's just random?
Initially it's just random, yeah. So these enumerated parameters are also used. Remember I mentioned that the components of the model can be optional as well. So whether or not included TP could be represented by enumerated parameter here. And so that's part of the way we choose that as well.
So in what cases does it happen that you don't want to include the TP?
There's some data sets where a first order model is sufficient, and you can actually learn quite a bit faster a first order model, but have a simpler model without a TP.
And same question about enabling SP learning.
That's a contrived example there. We don't actually search over that today.
Okay.
In our swarm.
Do we always have it on then?
I think we have it on for prediction models, but anomaly models, I think we leave it off.
Right, okay.
Okay, so now the other component that swarming has to figure out is which fields to feed into the model. And this is another set of logic, separate from scalar and enumerated parameters. So each field combination is basically a different parameter space. And so what happens is when I showed the PSO, we're running a bunch of particles and figuring out where they find the local minimum. We run a whole set of models in a PSO for each field combination. So there's dozens of models run for each possible field combination that we evaluate. And what we do is we run these, we're calling them sprints. So the first thing that happens is a bunch of single field models are created. In the example I showed, we had consumption, timestamp, and temperature fields, for example. We would run a bunch of models with temperature only, or a bunch of models with consumption only, etc. So these are single field models, and these, so we call it sprint 0. So, for example, when only consumption is fed into the model, there's a bunch of models run, and we search all the scalar and enumerated parameters to figure out the best set of parameters when you have just that one field. So the result of this is we can figure out which single field did the best. Once we have the best model here, we can figure out, well, say it happened to be field A was the best single field model. So we take that, we build up a bunch of two field models. So we take the best field from here, and we start making two field combinations. So each one of these has field A in it, but we add in one of the other fields as well. This is sprint number 1. And then we keep continuing this. It keeps continuing, building up bigger and bigger field combinations until the error score stops getting better. And that's when your swarm finally ends. Typically, you end up with most 3 or 4 fields before this decides to stop. Okay, so this is more of an advanced topic. There are ways you can customize the swarm. When you feed in a JSON file like I showed earlier, it actually creates 2 files transparently to you. description.py and permutations.py, and runs off of these files. If you want to run a more advanced swarm, you can edit these files that are generated and tell swarming to run directly off of those files. The reason you might want to do this is that there might be different parameters that you want to swarm over. There might be some that you want to hard code. There may be some that you want to change the range that they can be. And all this is available by editing the permutations.py.
So if you're familiar with your data, this could be really useful.
Yes. Yeah. Let me look at, we'll look at one of these permutations.py files to give you an idea of what's available in there.
And where do you specify the data file?
The CSV file? That's in the description.py.
Is that generated by?
That's also generated by, when you feed in the JSON file, it generates both description.py and permutations.py.
But can you run it without the JSON?
Yes, you can run it without the JSON. So if you call run swarm and you provide the path name to a .py file, it assumes that's a permutations.py file, and it assumes the description.py is in the same directory. So this is the permutations.py that was generated when I fed in that JSON file earlier in the presentation. Just a kind of brief overview. Here's an example of an enumerated parameter. This is saying try both this type of model and this type of model for inference type. In here you'll see examples of scalar parameters. So here's an example where the radius can be anything within 0.5 and 12, a floating point number between 0.5 and 12. Here's an example where it can be a floating point number between 1 and 6. Here's one that has to be an integer, but can be between 28 and 521. So you can go in here and change the ranges. You can actually add new variables that should be permuted over. You can hard code some of these if you don't want to permute over them. A lot of flexibility here.
So does, when this file is generated, I guess it looks through the data first to come up with these values? Or?
No, these values are pretty much hard-coded into experiment generator.
Okay.
Just kind of heuristically figured out in the past. They're not data dependent on your data file. The fields, I mean, which encoders are placed in here, of course, is based on the field names that you've provided.
Right.
But these ranges are just heuristically figured out one time in advance.
I'm just wondering, like, what for consumption, for example, is it there's a range between 28 and 521, or at least is that really saying that's the expected range of value for that field throughout the swarm?
Oh, this is not for the actual value of consumption. Okay. This is the N for the encoder. This is the number of bits that we're going to use in the encoder for that. Yeah.
So, Ron, is that really the range, or is it just those two values?
It's a range. It's a range.
And how, I mean, does it go like every one unit, like 28, 29, etc., or is it a few?
What happens is when you create the initial particles, they're just evenly distributed.
Oh, right, that's part of
in
the
that
algorithm.
space. Yeah.
Okay.
Yeah.
So it might not, it probably will not go every one.
Yeah, no. Yeah, and if you have a large swarm, it'll create 15 particles, so you'll cover that space a little more finer than you would with a medium swarm.
This might bring up some questions from people because there's been some discussion about N and W on the mailing list and what those mean and where they come from. So.
Well, N is the total number of bits the encoder is outputting. So if it ended up being 521, you'd have a 521-bit vector coming out.
Right.
W is how many bits are ones in that. So today we experiment generator always puts 21 for W. for every field, but we do try different values of n. And then the associated description.py, I'll just kind of briefly show that. This also is generated, and you can also edit this. This is basically the complete model description. And in here you'll find all the parameters for the model, and you'll see parameters in here that are go a little further down. For example, here's a parameter that's set to 32. That does not show up in the permutations.py because swarming is not trying different values for that. But if you wanted to, you could just add it in this dictionary as another parameter to consider in your swarm.
Oh.
It's just looked up by name, so it's pretty free format here. You can just add in new entries as dict, and it'll look for the associated entry in the description.py and plug in different values for it.
You could try different random seeds.
You could try anything in here, yeah. Anything that shows up in this file under a dictionary can be permuted over.
And that dictionary, for those who are familiar with the hotgym.py example, it's very similar to the model params.
Yes,
dictionary.
yes. Yeah. And then the data file, it shows up here in description.py. So this is the path to the data file it's going to use. So everything that was in that JSON gets put into this file in some manner or form, and you have the option to go and edit this after it's generated. So we talk about that. So you can edit that. Okay. So if you have chosen to take this route, all you got to do when you call run swarm is feed in the path to a .py file. And it knows if the extension is .py, it knows you're feeding in the permutations.py instead of a JSON file. And it'll skip this step here of generating it. Yeah, so any questions now? We can go through that, but that's the end of the presentation.
Yeah, but might be helpful to, so where are the main files that run swarm?
They run swarm.
And roughly what do they do?
Yeah. Okay. So this is the NuPIC repo here in the Pi directory. Pi NuPIC swarming is where all the source files for swarming are. The entry point is this permutations runner.py. The run swarm tool itself is a very small shell that calls permutations runner main. So permutations runner is the main module that initiates everything. It uses some helper functions in here. These two, dummy model runner, dummy worker, are just used for unit tests. Hypersearch v2 has the guts of the swarming algorithm. So that's where you'll find most of the logic to create the particles and figure out how they move and create new models and figure out which field combination should be tried next, when the swarm should end, and all kinds of stuff like that.
So a little history, because I know someone's going to ask, why is this called hypersearch?
Hypersearch was the original name of swarming. The engineering created name
Right.
before marketing.
The code name.
The code name, yes.
Okay.
Yes. Hypersearch v2 dump is a utility function that isn't used when you run a swarm, but it's helpful. You can point it to a MySQL database, and it'll extract all the model information that was created for swarm and create a nice spreadsheet file out of that. It's very helpful when you're trying to evaluate what happened. Hypersearch worker is kind of the shell of the process, the swarm worker process. And it calls into Hypersearch v2 to do all the heavy algorithm lifting. So this algorithm generic, this code here. And these are kind of helper functions for running a model, these three here. And permutation helpers is, some of the PSO logic is in here. This is kind of actually the very low level guts of the PSO. And you'll see in here you'll see the velocity equation that was in the presentation that is evaluated in this module here.
Could you show the wiki page you made?
Yeah.
Just for reference?
Yeah. Okay, so on the NuPIC GitHub site, in the wiki, there's a page titled Running Swarms. It covers a very high level what this presentation was about, but doesn't go in as much detail about the PSO algorithm as we went through in this presentation. But it does it does present what you need to define a swarm, the fact that you need MySQL available. It tells you how to run the example and what you should expect to see as output. It describes the files that are generated when you run a swarm. It goes through the swarm description JSON file, kind of like I did here, each section and the purpose of each section. The format of a data file. It gives a very rough overview of what is happening in the swarming process, and talks about how to run a swarm using permutations.py. And the other thing, which I didn't talk about in this presentation, is that it also describes how you can provide a custom error metric. So I actually didn't mention that, but by default, what happens is your model is evaluated using a average % error. So it's your how far was the prediction away from the actual as a percentage. If you want to, you can change that, use a different error metric. For example, you might want to evaluate the square of the error between actual and prediction. And that is an option you can do by adding a section to your JSON file with your custom error metric. And you have quite a bit of freedom in there. You can have a one-line function like this, or you can get fancy. This shows something quite, a little more elaborate. There are constructs you can use for storing intermediate values that your custom error metric might want to reference later. And this shows, one example of how to do a metric, of this form here. Yeah, so that's all in the wiki page. Cool.
Thank you.
Yeah, thanks, Ron. It's very helpful. So if anyone's watching and has any questions, you can go to our mailing list, go to numenta.org. There's an email address and links to our mailing list. Thanks again, Ron.